share my screen. And as you can see, a good 74 persons have submitted answers. And I think the overwhelming 70% versus 30% is for a pre-recorded worked examples released following the lecture progress and Q&A during consultation hours, discussion board, and email. So I guess that's basically what we'll be doing. So I'll ask the TAs to prepare pre-recorded work problems that will be released alongside with the problem sets. A small delay, but in principle, not long after the release of the problem sets, will we also provide pre-recorded worked examples so you can use them to guide your studies. And then any questions that you may have during for these worked examples, we will open topics in the discussion board, and we will also allow you to have, you can always ask questions during the Q&A, the consultation hour, and so on. So for those who are interested, I have updated if you go to contacts, you will see that the consultation hours are actually listed here. One thing I haven't appreciated is the best means to do so. If you go to Zoom, this should be doable. If you go to Zoom, then you should see two. It all works out. You see two things, right? One is digital classroom, one is exercise class. And what I'll try to do is I will have the TAs use this exercise class meeting, which they can open without my intervention, for the consultation hours, if should that be needed. Okay. Now there's this one little awkward thing which I don't think we can change now, which is not ideal, but Patrick's consultation hours is Tuesday, but somehow Alan and Isaac ended up with the same consultation. So effectively, you only have two consultation hours, and I'll ask them to each take turns to man the Zoom room during consultation hours. Okay. So any questions about this? None at all? Yes, that is. Yeah, let me get started. So let me share the screen. This thing here. Okay. Let's see. See. Is the bottom part being cut off or not? Okay, you can see the bottom part. Good. Okay. This is very clumsy, but basically working on two computers. Okay, so let's start with a recap. Okay, every lesson I'll try to start with a recap. So what did we do last time around? Well, last time around, we basically focused on fields. Okay. And in particular, we pointed to two particular fields that are of particular importance. So the first one is fields using scalar fields, vector fields. And a field is nothing more than a physical quantity that is defined throughout space. Okay, so in this case, you can have a scalar, like the temperature, that is defined throughout, in this case, our Earth. And so at every position on our Earth, we can associate a particular temperature. This could be an instantaneous temperature, so it's also a function of time, or an average temperature, which again is actually technically also dependent on time. Okay, and so the reason why I make this distinction now is because we want to focus. Okay, we're going to focus on electromagnetism in terms of fields. This is as opposed to kind of forces. A little bit do away with forces, and instead we're going to really focus our attention to fields. And in EM, right? EM, we have E field and E field, electric field and the magnetic field. And these are related to each other. These are specified using Maxwell's equations. Okay. And these could either be integral form or the differential. Now, can someone remind me, let's say remind me, but can someone mention the difference between using, let's say, the integral form versus the differential form of the Maxwell's equations? A minute or two. Over some surface volume versus an infinitesimal local point. Correct. Region considered is not the same. Yes. So, I mean, again, you can make them consider the same region, but it's more or less the technique, right? In the integral form, you have to specify the surface, and it's over some surface. Whereas if you look at the differential form, you can specify the field at a particular point, and then do your calculations there. So that's really where the big difference is. Okay, so I would say it's local, non-local versus local. Good. Okay. So and then once we've specified this, we've looked at the electric field, which turns out to be simply defined as as we move along. So if we take E as a function of R, right? It's a position vector, where in the limit of Q goes to 0, 1 over Q, and F force over Q. And so for this is then typically you can either you can then write this as Ke, which is the constant, right? It's just 1 over 4 pi epsilon naught, and here we can do the integral over some small charge, r minus r prime, and then here is r minus r prime. Okay. So this is over an extended, charge distribution. Of course, if it's a single charge, then we can, oops. If it's over a single charge, you can just write Q there instead of doing the integral. This is in terms of the electric field, and it should come as no surprise that today we're gonna take a look at the magnetic field. Now let me just make one more note here, and this is really from Coulomb's experiment. Okay. So next up, what we want to cover is the magnetic field. And in terms of the magnetic field, there's really been two critical experiments that were done in determining the existence and even the shape and form of the magnetic field. So the first one is so-called Ørsted's theorem experiment, and I will do justice to the original, to the proper spelling, but typically most languages do not have this O and a little dash through it, and it's typically written as OE. Experiment. Okay, Ørsted experiment. So basically what happens here is, this person, Ørsted, had considered some wire through which he put some current through. This wire, what he did is he then held a compass close to this wire. So let's imagine that he put a compass, let's call the compass as a circle, and let's give it a different color. Okay, so this is the compass. And what he found was the following. If you put the compass, if you put the needle perpendicular to the direction of the current, so let's put it here, then nothing happens. So in this case, whether you switch on or switch off the current, the magnetic needle does not move. So here, nothing changes. But the curious thing that he found is that when you do the same thing, again, this is the current, I, and when you do the same thing, that is bad. When I do the same thing, but now I put the arrow parallel to the current, then something does happen. Now I think for everyone who has done the who's done 2041 should at least be able to say what happens here. If I flip on the current, then this, what happens to this magnetic needle, to this compass? Anyone want to give it a go? Flip to point down. Indeed, okay. It flips to it being perpendicular to this to this current, and again, so on top of that, the fact that he saw it flipping from parallel to perpendicular, he also noted down the exact direction. And indeed, homing identifies it correctly. So what happens here is that, let's see, something dashed. Let's see. That's fine. Oh, okay. Let's use modern technology. So indeed, here, what we see happening is that compass still goes perpendicular. And so when he actually noted it down, right, when he did this experiment in a more systematic way, he ended up finding that, and I'll actually use this side now. So this is the current again. Current. And what he found is that the magnetic field actually forms a circle around this object. So let's make this here. Really loving technology. If you normally see me drawing circles, then you'll understand why I appreciate technology so much. Okay, sorry, 1 second. Fan started kicking off. Okay, so what he noticed is that the magnetic field has a particular direction, and so it goes around in a circle, and actually has a particular direction. So this is the magnetic field that he noticed. Indeed, here, magnetic field forms circles around the wire. And if you want to write it down mathematically, I can say that B arrow here equals to some scalar function, some scalar quantity, and then in some theta direction, where the theta is just the angle around this loop. So that's the first thing. That's Ørsted's experiment, and I think most importantly, this experiment noted the direction, the form, and the direction of the field. The next experiment that I wanted to briefly discuss with you is Ampere's experiment. When we take Ampere's experiment, this is probably much better known, this experiment, where what happens here is that Ampere reported the force between two currents. So what does this mean? So imagine I've got two currents side by side, and let's just call this 2. This is current 1. Okay. And in fact, I'm going to write I1, I2. I'm going to give it direction L1 and L2. It's just the direction. And then what happens is that there turns out to be a force here. Let's draw this one here. Then it happens to be a force going in this direction. This is F12. So what he noted was indeed that the force F12 of I1 on I2 was given by the following. F12 equals 2. In this case, it's minus some constant, and we'll define this constant later. And I got I1 I2 L, which is just the length, this here, L, divided by the distance between 1 and 2. And here is R hat 1, 2. So indeed, from this formula, we can see that the force is attractive when the two currents are in the same direction and they're repulsive in the opposite direction. Now, the need for this minus sign is because R12 is defined from is defined from the first current to the second current. And so in order to make it an attractive force, we need it to go in the opposite direction. That's why we have a minus sign here. Now, this constant is basically experimentally verified or is somehow defined. So if I take Km equals to 2 times 10 to the minus 7 newtons per ampere squared. Okay. So in this case, this is a positive constant in order to make the attractive and repulsive properties of the two wires. So in this case here, A is just the unit of charge. Charge, which is named after Ampere himself. Now this K is typically written along the same line of the electromagnetic constant, but now it's written as mu naught over 2 pi. 4 pi, I don't know why I say 2 pi. Now, the reason why this is mu naught over 4 pi instead of for the electromagnetic case, for the electrostatic case is 1 over 4 pi epsilon naught, becomes a little bit clearer later, but it's merely contingent. Okay? You don't have to worry about it too much. Okay. Now, indeed, as we look, this force is attractive if currents are parallel. So this is the second important experiment. And what we'll do is we'll combine these two experiments together in order to observe the magnetic field, or at least quantify the magnetic field. Because from the first experiment, from Ørsted's experiment, we know that if this wire I1 should be producing a magnetic field. Okay? If I take pow, so oops, this here is before. Right? So if I combine Ørsted's experiment, which is a straight wire, or any wire in a current creates a magnetic field, then Ampere's experiment shows that it actually produces a force. So I can combine these two to actually study the magnetic field. Okay, so let's take a look. Magnetic field has certain properties that we will discuss now. So the first thing I want to mention is that in the field picture, okay, so last time we focused on the field picture instead of the force picture. In the field picture, what happens is that the current I1 is the source of magnetic field. And then from Ørsted's experiment, experiment. Know that B1 is going around the wire. Now I can take a look at, at this slide over here. Now in the field picture, I know that this force is sourced by the magnetic field that one is creating, the current in one is creating. So somehow in this formula over here, I should be able to distill the portion that is associated with the magnetic field. So one identification that I can make is that this B field is given as follows. B1 equals, in this case, the magnitude and then the direction equals to Km I1 over R12 theta hat. Okay. So basically what I've done is I am taking this portion out. Take this one out, this one, and this one. And I'm associating that with the magnetic field. Okay, I haven't taken the R theta, R hat 12 yet. I'm here actually because I know it should be theta in a theta direction. So now, if I indeed use this field picture, then I can say that the force in I2 caused by B1, which is produced by I1. So in this case, F12 was minus I2 L. Okay, this is the length of the wire. This is the modulus, and then R hat 12. Okay, so we have these two expressions. Now they don't fully yet allow us to distill B. In order to do that, we actually make a few minor minor rewritings. And the first thing that we want to do is here we just express R hat 12 in terms of L2, the direction of the current 2, and E theta here, which in this case we can simply write minus 12 equals, and let's take a look. Okay. Now last time I also discussed the cross product. So in this case, what do I have? Well, I have that in green, this is the direction of the field. L2 points up, and R12 points outwards. So if I want to express R12 in terms of L2 and the direction in theta, so the direction of the field, then how do I do this? So in this case, minus R1, R2. I'll give you a minute to think about it, and feel free to, if you have the answer or if you think you know the answer, then put it in the chat box. sorry, I was muted. I see that Calvin said cross product. Can you be a little bit more specific? Again, I just want to stress with people here, please use your full name in your Zoom credentials. This just helps us identifying the students, and also just to make sure that we're not getting unwanted visitors. Someone wrote it fully in LaTeX. That's very much appreciated. I was going to say that for Chen Long, if you want to write it like that, then I wouldn't put the hat over this subscript. Just a small LaTeX thing, in case I would put it hat over the L and the E, and then the underscore. Otherwise, the hat looks kind of over the whole object instead of just over the E. I don't know. I like that. Okay, L2 cross product, E theta. Okay, indeed. This here I can indeed express as L2 times, okay, very tempted to write a hat, so L2 times theta 2. Okay, so that we can now use, right? Now, another thing that I can do is I could also express E theta in terms of L1 and R hat 1, 2, which is just E theta plus L1 hat. Right now I'm doing cross product R hat 1, 2. So if I now put all of this together, I can indeed write R hat 1, 2 equals L2 cross L1 cross R 1, 2. Now, why am I doing it this way? Well, that is so that I can write the force. I can simply write the force 1, 2 as this constant here, I1, I2L, length R1, 2. Now I can write L2 cross L1 cross R1, 2. And this helps us to identify what in such a way that I can now write B1 equals to Km I1 over R1, 2 L1 cross R hat 1, 2. And finally, the force in 1, 2 can then be written as I2, the length of I2 in the direction of I2 cross B1. Or, if you will, in general, it's just the force on some wire with a current I, length L in the direction of L hat this. So now we're getting a handle, right? If you look at this expression over here, we're actually starting to see the outline of the of the magnetic field. And that is good. Now, So now comes a little bit of a leap of faith, okay? Because the next thing that I'm going to write down is the so-called Biot-Savart law. And this Biot-Savart law basically tells me what is the magnetic field. Okay, let's write that down. So what is the field of a generic current? And I'm just going to write element here. Is given by the Biot-Savart law. And this states that a small equals mu naught I over 4 pi. Okay, this is just simply the constant. dl prime, and I'll explain where the prime comes from. R minus R prime and divided by R minus R prime cubed. Okay, the prime in this case is simply the the coordinates. So if this is some element here, then here is just, the L, the prime simply states that the coordinates of this R, this is R prime. And R is just wherever I'm evaluating the magnetic field. And so in order to get this distance in this position, I have to do R minus R prime. Okay, now this is one for a generic current. Now, I do have a question here, and see, it's 13 past. Wow, we almost took 45 minutes already. Okay, cool. Okay. In that case, okay, let me just pose this question and take a 5-minute break here. So the question is the following. Why is the Biot-Savart law difficult to experimentally verify? Okay. So let's take a 5-minute break. We will reconvene at 5:18. Okay. Let's take a quick break, and we'll come back and we'll discuss the answer to this question. Of course, in the meantime, if you have, or if you think you know what the answer is, then just put it in the chat box. Okay. See you guys in a few minutes. Okay, let's more or less get going. So I see two answers given. The first one from Anson is in the current lab, currents used in the lab, typically around a few amperes, produces very small B field to be detected accurately, so the BOSFI law is hard to verify. That's one. I mean, it's not necessarily the smallness. We actually have very sensitive ways to now measure the magnetic field. I mean, just for example, the Earth's magnetic field is very, very small. And yet, still using a compass, we're able to measure it. So it's not necessarily to do with the strength. We'll get to this. And Zheng Ling says it's very hard to measure the B field of a small segment. That is correct, but well, okay. The question is just okay. I'll read the whole answer first. Is that it's very hard to measure the B field of a small segment. We usually measure the total B field produced by the total length if we measure the B field at a point. It is sort of correct, but not exactly what I'm trying to answer. And then, again, we'll get to the right answer. Han Chunyuan says, we are not sure which segment produces the detected B field. Same as above, indeed. Yep, that's more or less, indeed, is more or less the answer, but not entirely, not entirely. Field measured from the combination of all segments. Yep. So the answer that people give is I would say more or less correct, but not entirely. Okay. I want to give out the steady curve. That's correct. I want to, well, we can consider the following, right? So indeed, everyone's answer is more or less correct. I wanna make sure that there's some distinction. Right? So indeed, if I have some current here, and I have some current, then I have some current here, and indeed it would be difficult to know. Okay, well, if I take this small element and I'm here, well, what is the isolated effect from this thing here, and not integrating this and so on. That's true. That's true. And this really has to do with two things, right? One is indeed, as Chung Chi is saying, is that because we're considering steady currents, we're always in a situation where current has to be flowing continuously, right? There has to be more and more. Every time I look, there has to be current flowing in a particular direction. So it's not like something I can just say, I isolate a small section of current. Right? Something has to keep flowing in order to maintain a steady current. So it's impossible to just say, okay, well, I'm creating some experimental setup where, where I can do this and this. Okay. Now, that's one part of the answer. The other part is, of course, how would I create? Is it at all possible to create a setup where I could, maybe get some small segment out? Like imagine the following. What if I do this? And I just do this and something like this. And somehow I make this very, very pointy. Okay, well, maybe it is, maybe I can measure just from this small segment over here. But is it realistic to be able to, fabricate this in such a way that the magnetic field from this part and this part do not contribute? And it being physical, right? Because it has to be physical, because there has to be a steady current flowing through here. So that's where the difficulty lies, right? It's not necessarily that, it is, it is because we're considering steady currents. Something has to be connected. We cannot construct an isolated, segment of steady current. And then plus, can we shape it in a particular form in which, the effects are only felt through this thing, but not necessarily through other wires. And that is the difficulty, the experimental difficulty. Because in the end, yes, for this one, the field may be going in a particular direction, but here at the edges, it actually flows over, goes like this. So, it would be hard pressed indeed to identify what part comes from the long edges and what part comes from the short edges. Okay, so that's indeed why the Biot-Savart law is so difficult to prove or to experimentally verify. And that's why actually it was Ampere who first did it with 2 straight wires. And then it was deduced. This relationship, the Biot-Savart law, is then deduced from it. And so unlike the Coulomb's experiment, where you can directly say, okay, well, this is how much charge there is, and I can generalize that to it coming from like a single point, and I get the explicit relationship out there. In this case, I can't, right? The most realistic thing you can do is 2 straight wires and then measure the force. And somehow you must then be able to distill this relationship from that. The exact way of doing it is a little bit cumbersome. And for the for the flow and for things that we haven't covered yet, I don't want to show you the full derivation. This is something that you will have to, well, okay, you don't have to believe me. One thing that I'll ask the TAs to, in one of the worked examples, is to show from the Biot-Savart law that you get the correct expression if I put 2 straight wires. Okay, I'll ask them to show the other way around, not from Ampere's experiment prove Biot-Savart law, but instead, if I have Biot-Savart law, can I get at least the correct expression for Ampere's experiment? Okay, let's move on and let's take a look at the superposition. Okay. So for the for the electrostatic field, we also introduced the notion of superposition, where one part of the interaction between a field and some element, in this case a current element, is independent of all the other elements. And so superposition also holds. Superposition also for B field. Okay. So let's consider, in this case, n infinitesimal paths. And so the B field can simply be made out of the limit of d small element goes to 0 and n goes to infinity. The sum j equals to 1 to infinity. Okay. And this is simply then mu naught over 4 pi sum loop. Okay, assuming that indeed we keep some steady current in the loop. EL at cross. Okay. This cross product R minus R prime divided by this case, modulus of r minus r prime cubed. Indeed, again, the prime is along the path. Okay, so that's the magnetic field. Now we have both an expression for the electric field and the magnetic field. Now, I want to take a short explanation, not explanation, a short, little bit of a detour, and quickly discuss the notion of current first, and in particular, kind of how to relate this to the charge. I think this is something that most of you will have seen. So imagine I've got some tube, okay, and there's some current flowing through. Call that J, which is the current density, and it's flowing through some area dA. I can take some element over here, and I can basically say that it is some velocity, some density. Okay, so this is maybe some particle density. And this Q here, okay, let me give them all alpha, just in case there are particles with different charges. So this is just charge of type alpha. So indeed, in this case, the current is given by J equals N, the particle density times the charge of each of these particles times their velocity. Okay, and you can see this as some average velocity. Or in this case, the total is just J, total is just the sum of all the different types of particles one has. Now, at least in this definition, know that J is in direction of V if Q alpha is positive. Now we know from experiment that typically the thing that moves are electrons. And so it's a little bit done in a clumsy way where the current is not actually defined with respect to what is actually moving. Because the electron has negative charge. And so we end up, and this is just pure convention, right? Negative charge, positive charge is pure convention. And somehow we've managed to define the electron as negative charge, and so the current is in the direction of the flow of positive charge, and so the current and the actual stream of electrons are in opposite directions. It's a caveat I think most people will have seen some way or another, and but it's something to bear in mind. So now, what we can also do is now we can relate the Savart law, right? The force, the magnetic field, and therefore the force on a charged particle, as opposed to on some current. So indeed, the force on a charge, simply written by considering that, in this expression, I need I, L, L hat, which I can simply write as L hat, which is just the direction, integrating J dot L D. Okay? Right? So J dot dA is indeed the entire current that flows through the wire. And L is indeed the the whole piece that is going through. Now, L dot dA, or L times dA, is simply J dot dV, where V is some volume. Let's see if I got this right. Makes sense. Okay. And so I end up with the expression that I can now write that F is simply the integral of J cross B D. Or if you will, for some small f, for some small element, the force is just J. Now I can write J as a function of, well, I can write J in terms of V, the velocity, arrow here. So indeed, the ultimate, the ultimate expression is simply that it is 1 over some volume, okay, for small f, indeed, and then the sum of all alpha, all the different species, and then of course for all I in some volume V of Q alpha V I plus B. And here what we can see is we get back the usual expression where the force is just if I take a single particle, okay, so I don't have to integrate over some volume and I don't have to consider different species, different types of charged items, then this simply leads back to F equals QV. Okay, so that's the force on an individual charge. And again, it should be something that you have seen before. Okay, now this is a good moment to take another break. I do apologize, the first break did come a little bit late. But let's take a quick, again, 5 minutes break before we move on to the next topic. And yeah, let's reconvene at 5:41. Okay. See you guys in a bit. Jason, what do you mean last step? Step 1 over delta V, etc. Okay, so the very last step. So from here to here, we simply use this here. Actually, this should be okay. The 1 over V is a little bit superfluous. Yeah, the way I've written it, I don't think I need the 1 over V. Yeah, that was supposed to be the unit volume, but since I've already defined small f as to be kind of, the force in some small volume, I don't need to explicitly divide it again. But then I do need the n here. It's not necessarily on the entire charge, but it's on something small, like some volume element. That's answering Anson's question. That is, big F is the force on the entire wire, and small f is then, okay, I don't do the integral in dV, I just keep it in some small element, and then whatever here is just whatever exists in terms of charge and velocity in that small element. Okay, any more questions? Before I move on and start the last topic of today. Okay, if not, let's carry on. So I wanted to at least start today by now talking about the mathematics behind fields. Okay? Because we've seen now two expressions. One is for the electric field in terms of some charge or some charge density, and we've seen magnetic field here, the Savart law, as indeed the as in terms of some current density. But that by itself is just is not enough. That just merely states that what what made those fields look like. What do we really need in order to determine the properties of the field? And that is really what we're going to discuss now. So the first thing that I want to highlight is so-called Helmholtz theorem. This is Helmholtz. There's a T. It may not be a T. Helmholtz theorem. This theorem actually states something which is actually going to be important for what we are going to do. That is that any vector field, F, for those who are mathematically inclined, this does mean under the assumption that the field is finite, uniform, and continuous. Maybe expressed as follows. I'll come to the question in a moment. So this is what's the summation in I in that small volume means. So let's go back to the last one. So the question is here. This is simply, if I have some small volume, then basically if I further differentiate all the different I's, no, it's all the, like if in delta V in the small volume there are different elements, so that I is not, sorry, yeah, this is basically not taking delta V to infinity, to an infinitesimal element, and so that there could be different V's, okay? Different elements inside this small dV. Okay. Let's go back. So let's go back to Helmholtz theorem, and I'll read it again. It says any vector field F may be expressed in the following way. F can always be expressed as the gradient of psi plus the rotation of some A, which in this case, phi, or psi, is any scalar field. A is any vector field. And a small caveat is that the divergence A exists. Now, all of these words, and I promised that I was going to do things in, I was going to build everything from the ground up. So that's what I'm going to do. So I'm going to assume that, we don't know exactly anything yet. This is just the formal kind of theorem. And so first what I'm going to do is I'm going to actually explain to you what this means visually. Then I'm actually going to go term by term. So what is the gradient? What is the divergence? What is the rotation? What a curl? Then I'm going to go all the way back and prove Helmholtz theorem. But visually, what does this mean? Visually, I can actually state the following. I have any vector field can be basically decomposed into something that looks like the left hand, something that looks like this, and something that looks like that. Now this is actually quite a profound result, stating that like I can know the properties of any vector field, but just looking at these two patterns over here, this left and this right pattern. For those who have oh no, what happened here? So what does this mean? Well, it means that for any vector field, properties are known if you know the divergence, which is the right-hand image, and the curl, which is the left-hand image. So Helmholtz theorem, which is listed above here, is basically the manifestation. So indeed, what we're going to do next, and this may span some of today's lecture and maybe even some of next lecture, is actually going to take a look at this. Okay? What is the curl? What is the divergence? These are all these are all differential operators. I'm going to take a look at it. Okay, so the first thing that we look at is, in this case, is for a scalar field, and that is the so-called gradient. So the gradient only operates, so it operates on a scalar field and returns a vector field. Okay, so in Cartesian coordinates, these are coordinates that I think we should have seen before last time around. So it's x, y, and z. In Cartesian coordinates, the gradient is as follows. Gradient of some vector phi is just x partial phi partial x plus ey partial phi partial y plus ez partial phi partial z. Now this little thing over here, this guy over here, is typically referred to as the nabla or the del operator. So this, I typically put an arrow in front just because it helps me remember that, it more or less acts like a vector. This here is called del operator or nabla. Don't ask me why. I really hate the word nabla, so I'll try to avoid using it. And so in this case, you can actually consider this del operator in Cartesian coordinates actually as ex partial x plus ey partial y plus ez partial z. Okay. So whatever scalar field you put in, you operate on, just put in here, here, and here. Okay, now beyond what we know about this form over here, we can actually give it some geometrical meaning. Okay. And so let's consider that for any field phi of r, okay, it's just some general r. There are surfaces for which phi r equals a constant. And indeed, the vector nabla phi simply is perpendicular to phi r equals constant. So if you will, let's take a look at an actual picture. So imagine that this is a contour where phi equals a constant, and here is another one. There's another one. There's another one. Okay. So I could say that this is phi equals to 1, phi equals to 2, 3, and then 4. And maybe the best example here is a height map. For those who are interested or kind of hikers, if you have a map, you can kind of see, you can draw these contours of equal height. And this vector, nabla phi, is simply perpendicular. It points perpendicular to these phi equals constant lines. So here, if I take this, I draw a vector perpendicular, and this is the vector field created from phi. Therefore, you can also see that indeed, when we start with a scalar field, we can still produce a vector field by indeed doing the gradient operator. Now, as part of this differential operator, what I can also do is actually look at the differential change in the field phi. So if I now consider the differential change, or a small change in phi, I can simply write d phi. And through the chain rule, I know that it is partial phi partial x dx plus partial phi partial y dy plus partial phi partial z dz. I can simply write this as nabla phi in a product with dr, where in this case r is simply given by x dx plus ey dy plus ez dz. Okay. So indeed, if you will, this nabla phi, the gradient of phi, is a vector field. And in order to know how much the field has changed in some infinitely small direction, I just do a scalar product, right? I do the projection along some dr, which is what I'm interested in. And that gives you a small change of phi. So indeed, if I look at the height, then let's say I want to know if I take a certain path down a particular road, and I want to know, okay, what is the height differential? And I can take a look at all the contours of constant height. I draw the various gradients, and I'm just saying, okay, well, how much is the gradient along exactly the line that I'm going to walk? And that will give me the height change. This is the gradient. So that's the first differential operator that I wanted to talk about today. Next one is the divergence. Now let's, divergence. Okay. Now what is a divergence? Well, the divergence is a operator that takes in, that acts on a vector field and results scalar. Okay. In Cartesian, we have the following expression. Coordinates. We have the following expression, that is that nabla dot a equals to partial a partial x plus partial ax partial ay partial y plus partial az partial z. In this case, indeed, a can be written as ax ex plus ay ey plus az ez. And hopefully you can now also see why I typically like to put an arrow on top of the nabla, so that this, I can really just think about it as a dot product. And if I go, for example, in this slide here, I can think about it as some constant times a vector. Okay. Now, I want to stress that for the gradient, but now also for the divergence, I'm only so far showing you the expression in Cartesian coordinates. And there, these look very, very straightforward. Right? It's just partial x, partial ax, partial x, partial ay, partial y, partial az, partial z. But and we'll go through that at some point later, and that is when we don't just do x, y, and z coordinates, but we actually have, let's say, spherical coordinates, then the divergence actually looks very different. We'll get to those when we discuss curvilinear coordinates. Okay, so just a bit of nomenclature. So if indeed the divergence of a field equals 0, then this is what we typically call a solenoidal. And the reason, or the interpretation, should become clear in a moment, because the next thing I want to do is discuss what geometrically, what is the divergence. And in order to do that, we need to do a little bit of a, we need to consider the actual divergence over some volume. Let's take a look. So let's try to come up with a geometrical interpretation of the divergence. And I'll skip all the way to the end, because I do think most people know this, but the divergence is simply the flow of a substance or property, or the flux of a vector field. So I want to make this part explicit. So let's take a look at some geometrical interpretation. So let's imagine that I have a cube. Now that I've got modern technology, drawing cubes actually looks quite nice. Look at this. Look at this. Gorgeous. What a cube. What a cube. I do think we need to take a quick moment to appreciate the beauty of this cube. Okay, now let's actually do the consideration. So I want to know what is, A, what is the change of A in this thing here. Okay. So let's take a look. Okay, I want to sum up the flux. Amount of vector field that goes out of these different surfaces. And I'm just going to name this surface 1. I'm going to name this surface 1. name this surface 1. I'll name this surface 2. And let's see, did I do this correctly? This is X, Y, and Z. Y direction. Sure, that's fine. Let's get this X, Y, and Z. Okay, so now I want to take a look at the flux through all of these 6 phases, but we're only going to consider 1 and 2 for the time. So in order to quantify the surface, I'm actually first defining ds, phase 1. The way I'm going to do this is I'm going to give it some area. I'm going to call dx dy, assuming that this is indeed y dx z. And I'm going to make it point, right? I'm going to make it point into the y direction. In this case, it's the negative y direction, right? If the positive is in the other way. In this case, we have all defined them to be outwards, all these surfaces. So now the vector field going through this phase, and again, assuming that this is an infinitesimally small surface, is just A dot ds. I'm just going to, again, assume this is phase 1, which is simply ay ey dot minus ey dx dy is just minus ay dx dz. Okay, so far so good. Okay, so in this case, I'm assuming that this is phase, like I assumed that A is defined with respect to just the origin. So let's take a look at the flux of the other side of phase 2. So for phase 2, what do I have? Well, I still have A dotted with the S, and now phase 2, which if I define AY with respect to phase 1, then I have AY plus some change, the AY partial Y, right? The change is only in the Y direction, dy. And y dot ey dx dz. Now, 2 caveats here. One is, of course, this is just ay plus some change in ay, okay, where this is just to change from phase 1 to phase 2. Now, this thing over here, is a positive sign because we don't need the negative sign, right? It points in the y direction. I'll go back to this figure over here, and indeed, if I take y to be going to the right of me, then phase 1 is pointing in the negative direction, phase 2 is pointing in the positive direction. So okay, so I've got this expression over here. Now I can make this equal to ay plus partial ay over partial y dy dx dz. So now indeed, if I call a dot ds, if I just give it some scalar, and I'm going to call this a flux, then I can now say that the flux and I say total flux, phase 2 minus phase 1. Okay, is now given by D. I'm going to give this a capital phi y equals partial ay partial y dx dy dz. Okay. So indeed, if I look here, the x and the z are here and here. The y comes from here. Ay cancels with this one over here. So if I do phase 2 minus phase sorry, if I do phase 2 plus phase 1, I have to say plus because I do put the signs incorrectly. Then ay cancels out with this ay over here, and the only thing I'm left with is partial ay partial y. Here I got dx dy dz. Okay, so now I can do the same exact thing for the other ones. So I got d phi x, which is partial ax over partial x, dx dy dz, and I got d phi z equals partial az partial z dx dy dz. Now if I take the total sum, the total flux is just the sum over all phases of A dot ds, just call them I, all the different phases, equals to partial ax over partial x plus partial ay partial y plus partial az partial z of dx dy dz, which is given the same as nabla dot a with some small volume dp. Okay, so now this is asking us for some interpretation. So I want you to focus on this part here. This part here. So imagine now I've got some volume, and I've got all these different phases. Now what I've calculated is the change, the total change over all of these different surfaces. Let's go back to this figure over here, and let's focus on this figure here. I have now calculated A that goes out here, that goes out here, that goes out here, that goes out there, that goes out here. Now imagine I put in a constant vector. Okay? So I've got a vector that doesn't change, that remains constant, and let's say it pierces through the phase 1 and phase 2. So imagine I've got something like this, and it's just something that pierces through this. Now if I calculate the flux for this thing over here, just this vector, then what is the flux? If it's just some constant vector going through this. Give you a minute or two to think about this. Up, 0. 0. Okay, so indeed the answer is 0. You can think about it in the following way. In this case, the two sides here, and this vector points into my volume when it comes in, and when it goes out, it points out. So they have opposite sign, but they're the same with respect to ds on this face and ds on this face. And so if the vector doesn't change, then indeed passes through. In one side it's a positive sign, and one side it's a negative sign. When I add all the faces up together, it cancels out, it goes to 0. So the only time when it's not the same, right, when the divergence is not the same, is when it doesn't stay constant. Something must be, in a particular language, something must be diverging. Okay? Now you can also say, okay, it's negative of converging, it doesn't matter. So you can see it in the following sense. So I'm now drawing just some generic surface here. If something goes through straight like this, then the divergence equals to 0. Right? Because it's the same element, same vector that goes in as the vector that goes out. The elements cancel. So there must be, in order to get a non-zero divergence, something must be diverging. Right? So the vector field can no longer stay parallel to each other. It must be somehow diverging or converging. Depending on the sign that you pick, you could have equally said convergence instead of divergence. So indeed, by looking at this kind of, by taking this almost like a geometrical meaning, where where nabla dot A is just the flux over some volume, we have more or less given it some interpretation. It's the degree of divergence of the field lines, right, of these vectors. So somehow they must not be parallel, they must somehow diverge. Now we can go back to this image over here. This one over here. Right? If I now look at the right image. So if this is, if in the middle, if in the center there's some volume, then we can kind of see that this is almost the way of maximum divergence. Right? Every point, you can think about it in the center, and then every point goes outwards. They all point in exactly, as far as possible away from each other. That there's no component that remains parallel. So that is the divergence. So if in the right-hand side, that image is something that only has a divergence. Now you can more or less guess where we're going to in the beginning of next week, and also why, if I say that the divergence equals to 0, if the divergence equals to 0, then it's called a solenoidal. That is exactly for this image over here, because if it's completely divergentless, it has nothing of the right-hand side, and it only has the left-hand side, and this goes around like a solenoid. So that's the image of a divergence. Okay, it is all these vectors that go outwards. Okay, I think this is pretty much all the time that we have today. Let me give a moment here to see if there are any questions about all the material that we've had so far. Okay, going once. What is the app that I use to take notes? So I actually sometimes use a Linux system. This is actually a Windows system, and this is something. Well, okay. Why don't I do the following? I'll see if there are any questions regarding the actual material, and then I'll come back. I'll stop the recording. I'll come back to your more kind of less relevant for the course. But yes, Anton, I'll answer your question. Any questions regarding this thing over here? Going once, going twice. In that case, I am going to stop the recording now.